After going through this lecture, we should be able to write the major products for the following reactions. Similarly, we should be able to write product as well as mechanisms for these Baeyer Villiger rearrangements. In this lecture, we will discuss Baeyer Villiger oxidation of ketones. The oxidation of ketones into esters and cyclic ketones into lactones by treatment with peroxyacids is called Baeyer Villiger oxidation or Baeyer Villiger rearrangement. For example, when this ketone is treated with peroxyacid in the presence of dichloromethane, ester is formed. The oxygen from peroxyacid is inserted between carbonyl carbon and alkyl group. Likewise, this cyclic ketone under similar conditions forms this lactone, with oxygen inserted between carbonyl carbon and adjacent methylene group. If we analyze the structure of peroxyacid, the hydroxy group is the nucleophilic part and this acetate is the good leading group. In the first step of the mechanism, the carbonyl group is protonated by peroxyacid to increase its electrophilicity. The peroxyacid functions as a nucleophile and attacks the protonated carbonyl group, forming a tetrahedral peroxide intermediate called Regioselectivity intermediate. This peroxide intermediate then undergoes loss of carboxylate anion and migration of a group from carbon to electron-deficient oxygen to yield the protonated ester. The carboxylate anion is resonance stabilized. This alkyl migration and the loss of the carboxylate anion both take place in a concerted process. It is assumed that the migrating group has to be in a position antiperiplanar to the dissociating oxygen-oxygen single bond of the peroxide. Finally, the carboxylate anion abstracts a proton from protonated ester to form ester and corresponding carboxylic acid. In case of unsymmetrical ketones, the Baeyer Villiger oxidation is regioselective. The regiochemistry depends on the migratory aptitude of alkyl Aryl groups attached to the carbonyl group of ketone. The approximate order of migration is: tertiary alkyl group is the best at migrating, then secondary alkyl group, which is closely followed by Aryl group, then primary alkyl group, then methyl. This roughly follows the order in which the groups are able to stabilize a positive charge. Consider, for example, this alkyl Aryl ketone. The treatment with peroxyacid will form this peroxide intermediate. The migration of phenyl group to oxygen will form this ester with oxygen inserted between phenyl and carbonyl carbon. Alternatively, the migration of R to oxygen will form this ester, with oxygen inserted between R and carbonyl carbon. The percent yield obtained for different alkyl groups has been calculated for this reaction. For R as methyl group, this ester is obtained in 90% yield, whereas this is not obtained at all. This means phenyl group has quite higher migratory aptitude than methyl group. Similarly, when R is ethyl, this ester is obtained in 87% yield, whereas only 6% of this ester is obtained, indicating that Aryl group has higher migratory aptitude than ethyl group. When R is isopropyl, the percent yield of this ester decreases to 33%, whereas that of this ester increases up to 63%. This means the migratory aptitude of isopropyl is slightly higher than phenyl group, and both groups compete for migration. When R is tertiary butyl group, this ester is obtained in 2% yield only, whereas this one is obtained in 77% yield. This clearly indicates that tertiary butyl group surpasses the migratory aptitude of phenyl group. Now the question is, why a more substituted alkyl group migrates faster in Baeyer Villiger rearrangement? To understand this migratory aptitude, consider for example, this unsymmetrical ketone with methyl and isopropyl groups flanking the carbonyl group. Upon treatment with peroxyacid, the peroxide is formed. As discussed in mechanism, migration of alkyl group, breaking of peroxide OO bond, as well as reformation of CO pi bond is a concerted step. Thus in the transition state, let us show the breaking of CC bond and peroxide OO bond with red dotted lines, whereas the formation of new CO sigma and pi bond with green dotted lines. During this migration, the migrating carbon of alkyl group develops positive charge as the carboxylate anion departs. The more substituted alkyl groups stabilize this positive charge better, making the transition state more stable. The more stable the transition state, the faster the rearrangement. Thus oxygen from peroxyacid is inserted here, between carbonyl carbon and isopropyl group. When a benzene ring migrates, pi participation is involved as the benzene ring acts as a nucleophile and the positive charge can be spread out even further. What was a transition state in alkyl migration becomes an intermediate in phenyl migration. This intermediate loses a proton to restore the aromaticity of phenyl ring and forms the ester. Note that the phenyl group is stabilizing the charge here, like a pentadienyl cation rather than like a benzylic cation. Consider that this Aryl group has group Z attached. It should not surprise us that electron-donating groups such as methoxy group stabilize the positively charged transition state and increase the rate of reaction, whereas electron-withdrawing groups such as NO2 destabilize the transition state and decrease rate of reaction. Thus, for para-substituted aryl groups, migration order is para-anycyl migrates in preference to para-toluol, which has more migratory aptitude than simple phenyl. This has more migratory aptitude than para-chlorophenyl, which has more than para-nitrophenyl, and so on. Based on this migration order, if we take this ketone and subject it to Baeyer Villiger conditions, the para-toluol group will migrate in preference to phenyl. Similarly, in case of this ketone, the phenyl group migrates in preference to para-chlorophenyl group. In short, the product can be written directly by inserting oxygen between carbonyl carbon and the group that has higher migratory aptitude. One point to note about this rearrangement is that the rearrangement step occurs with retention of stereochemistry at the migration center. If we consider this ketone, which is the syn-diastereomer, and subject it to Baeyer Villiger oxidation, the product is obtained in 63% yield with syn stereochemistry as in the reactant. Consider this benzylic ketone, it is expected that racemization would occur. But when it is subjected to Baeyer Villiger oxidation, benzylic group migration gives major product in 87% yield with 98% retention of configuration. By looking at the orbitals involved, you can see why this must be so. Let us write the peroxide formed by reaction of ketone with peroxyacid. We have already discussed in mechanism that when the pi bond is restored, the CC bond between carbonyl carbon and migrating group shifts to oxygen, so that the O peroxide bond breaks at the same time. Let us draw the orbital picture of bonds being broken and formed. Let us show this migrating benzylic group in blue and orbitals of peroxide linkage in green color. This is the filled sigma bonding orbital and this is the empty sigma antibonding orbital. Let us show this migration again here. Migrating group shifts to oxygen, carbonyl reforms, while peroxide linkage breaks. This forms the product ester like this, while carboxylate from peracid leaves. The sp3 orbital of the migrating carbon just slips from one orbital to the next with the minimum amount of structural reorganization. The large lobe of the sp3 orbital is used, so the new bond forms to the same face of the migrating group as the old one. And stereochemistry is retained. The orbital interactions in all 1,2 migrations are similar. Therefore, we can say that in all 1,2 migrations, the migrating group retains its stereochemistry. Now let us discuss some applications of Baeyer Villiger oxidation. Esters which are difficult to synthesize can be prepared by this method. For example, when acetophenone is treated with peroxyacid, phenylacetate is obtained. Similarly, pinacolone, on treatment with peracid, is converted into tertiary butyl acetate by migration of tertiary butyl group. When 1,2-diketones or orthoquinones are subjected to Baeyer Villiger rearrangement, anhydrides are produced. For example, this diacetylon treatment with peroxyacid gives acetic anhydride. The oxygen from peroxyacid is inserted between these two carbonyl carbons to form anhydride. Likewise, when this alpha-naphthoquinone is subjected to Baeyer Villiger oxidation, the oxygen is inserted in between the two carbonyl carbons to form this anhydride. With some condensed cyclic ketones, 2 lactones in varying proportions are formed. For example, when camphor is subjected to Baeyer Villiger oxidation, it gives 2 lactones in different proportions. This lactone in major proportion is the normal product, formed by the migration of the tertiary bridgehead carbon, while this lactone in minor proportion is formed by the migration of the methylene group. The reason for the formation of this lactone is steric factor encountered in migration of bridgehead tertiary carbon. Aliphatic aldehydes are oxidized to acids by migration of the hydrogen. For example, when this aliphatic aldehyde is subjected to Baeyer Villiger oxidation, the oxygen is inserted in between carbonyl carbon and hydrogen to form carboxylic acid. A few aromatic aldehydes have been converted to formates by the migration of the Aryl group in preference to hydrogen. Thus, benzaldehyde on treatment with peracid gives Aryl formate as product. That means phenyl migrates in preference to hydrogen. In case of this ethyl cyclohexyl ketone, oxygen is inserted between carbonyl carbon and cyclohexyl group. In case of this aliphatic aldehyde, hydrogen migrates in preference to alkyl so that carboxylic acid is formed. In case of this unsymmetrically substituted cyclopentanone, more substituted carbon migrates in preference so that this lactone is formed. Consider this cyclic ketone. When treated with peroxyacid, the bridgehead carbon migrates in preference to methylene to form this ester. Moreover, the product ester forms with retention of configuration. This metachlorobenzaldehyde forms Aryl formate with preferential migration of Aryl group compared to hydrogen. This ketone is C2 symmetric, so it doesn't matter which group migrates because both are same and will give same ester as product. The only care we have to take is to ensure retention of configuration. Don't be confused that stereochemistry of this methyl in migrating group is changed. It is still same as in the reactant, obeying the retention rule of Baeyer Villiger oxidation. The methyl is on wedge, rather than on dash, as in reactant, only because the group is drawn upwards. L-tyrosine, a relatively cheap amino acid, can be converted to the important drug L-Dopa, provided it can be hydroxylated ortho to the OH group. Since OH is ortho-para-directing, therefore this is where electrophilic substitutions of the phenol take place. But electrophilic substitutions with HO positive are not possible. The Baeyer Villiger rearrangement has solved this regioselectivity problem. If L-tyrosine is treated with acetyl chloride in the presence of AlCl3, Friedel-Crafts acylation takes place, ortho to OH, as para position is already taken. This acetylated L-tyrosine on treatment with hydrogen peroxide, in presence of sodium hydroxide, undergoes Baeyer Villiger reaction, so that oxygen from peroxide enters between carbonyl and Aryl group to form ester. This ester can then be converted to hydroxyl by hydrolysis. This means that HeMeCO positive can be used as a synthetic equivalent for HO positive using Baeyer Villiger rearrangement. Notice the unusual use of the less reactive H2O2 as oxidizing agent is possible only when the migrating group is an electron-rich aromatic ring. These reactions are sometimes called Dakin reactions. Let us check our understanding of Baeyer Villiger rearrangement by approaching this small conversion sequence. Benzene treated with acetyl chloride in the presence of AlCl3 gives product A, which upon treatment with meta-chloroperoxy benzoic acid forms two products, B and C. B is major and C is minor. B on treatment with Br2 in the presence of FeBr3 gives two product, D and E, whereas C under similar conditions forms only one product, F. Let us find the structures of A2F. Benzene on treatment with acetyl chloride in the presence of AlCl3 undergoes Friedel-Crafts acylation to form acetophenone as product. The acetophenone on treatment with MCPBA undergoes Baeyer Villiger rearrangement. The phenyl migration forms the major product, whereas methyl migration forms the minor product. This acetate group is ortho-para-directing, whereas this carboxylate is meta-directing group. Therefore, bromination of phenyl acetate forms two products, ortho and para-brominated products. Whereas methyl benzoate under similar conditions forms only meta-substituted product. Thus these products in the reaction sequence can be designated as, this is, A, which gives B and C. B gives D and E, whereas C gives only F.